Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Commence. The year 1973 witnessed the unveiling of seminal scholarship, authored by Vinton, Cerf and Robert Elliot Kahn, detailing a protocol for packet network intercommunication. This essay embarks on a comprehensive exploration of this foundational paper, subjecting its arguments, assertions, and proposed mechanisms to rigorous scrutiny. We delve into a systematic examination of its sectional composition, evaluating the merit of its claims within the technological context of its time and its enduring influence on the architecture of the Internet. The intention is to unpack a logical framework underpinning its design, assessing the paper's success in articulating a vision for a globally interconnected digital future. Section 1: Introduction and Underlying Principles. The paper initiates by addressing the burgeoning demand for interconnected computer networks, each operating under potentially divergent protocols. Cerf and Kahn posit that individual networks, while effective in their localized environments, presented interoperability challenges hindering larger-scale communication. Their introductory claims underscore the need for a standardized protocol suite capable of facilitating seamless data exchange across heterogeneous network architectures. A primary principle introduced is the concept of packet switching, a technique viewed as a more efficient alternative to circuit switching, especially for bursty data traffic characteristic of computer applications. The claim regarding packet switching's enhanced efficiency warrants careful consideration. While the architecture indeed offered greater resource utilization through statistical multiplexing, the increased complexity involving packet assembly, disassembly, and routing imposed its own overhead. The authors persuasively argue that this overhead represents a worthwhile trade-off when weighed against the benefits of increased network utilization and resilience. The paper lays groundwork for a novel approach to this challenge. These early claims establish a basis for the following sections in regard to the needs and methods for efficient network communication. Section 2: The Gateway Concept and Internetwork Addressing. A pivotal section introduces the gateway as the core element enabling internetwork communication. The gateway, later known as a router, serves as an intermediary, forwarding packets across network boundaries. Cerf and Kahn propose a hierarchical addressing scheme, enabling unique identification of hosts across the interconnected network. A claim concerning the scalability of this addressing scheme is essential to evaluate, since it is the basis for a global Internet. While the initial address space design proved sufficient for the early stages of Internet growth, subsequent expansion required the introduction of subnetting, classless interdomain routing, and the Internet Protocol version 6, IP6, each expanding addressing capabilities. The address scheme outlined in the 1973 paper envisioned a unified address space, the implementation of which requires standardized management to prevent collisions. The authors acknowledge the importance of distributed control, suggesting mechanisms for gateway coordination and routing table maintenance. The paper notes that the gateway functions as the point of interconnection between dissimilar networks, thus allowing the continuation of individual network protocols. The gateway itself would be running the Internetwork Transmission Control Protocol, which is further discussed in the following sections. Section 3: Internetwork Transmission Control Program Design. The third section presents a detailed description of the Internetwork Transmission Control Program, or TCP, outlining its functions, message formats, and control procedures. A central claim is that TCP provides reliable, ordered delivery of data across unreliable network paths. To achieve this, TCP incorporates features such as sequence numbers, acknowledgements, and retransmission timers. The paper asserts that the protocol is capable of adapting to varying network conditions, dynamically adjusting transmission rates to maximize throughput while minimizing congestion. The assertion of reliable delivery warrants close scrutiny. While TCP indeed incorporates mechanisms to detect and recover from packet loss, it relies on the underlying network infrastructure to provide connectivity in scenarios where network paths become completely unavailable. TCP's reliability guarantees cannot be fully realized. The paper discusses flow control mechanisms, preventing a fast sender from overwhelming a slow receiver. These mechanisms include windowing, where the receiver advertises the amount of data it is willing to accept. The initial windowing mechanism was relatively simple, with limited ability to handle large bandwidth variations. This limitation necessitated the development of more sophisticated congestion control algorithms, such as TCP Tahoe, Reno, and Cubic in later years. TCP is layered in a way that includes sequencing and acknowledgement to allow higher levels of transmission. The TCP design, as outlined in the 1973 paper, is the core of today's Internet. Section 4 Packet Formatting and Header Structure. This section focuses on the precise format of packets transmitted across the internetwork. Cerf and Kahn detail the structure of the TCP header, specifying the location and meaning of various fields, including source and destination addresses, sequence numbers, acknowledgement numbers, control flags, and checksums. The paper claims that this well-defined packet format ensures interoperability between different implementations of TCP. The claim concerning interoperability hinges on strict adherence to the specified packet format. Deviations from the standard, even seemingly minor ones, can lead to communication failures. In practice, ensuring interoperability requires extensive testing and validation, particularly when dealing with implementations from different vendors. The length of the various fields in the header, such as the sequence number and acknowledgement number, determines the maximum amount of data that can be transmitted reliably. The original 32-bit sequence number space proved sufficient for early networks, but increasing bandwidths necessitated the development of TCP extensions, such as TCP timestamps, to prevent sequence number wraparound. The paper also mentions the checksum field, used to detect transmission errors. The original checksum algorithm was relatively simple, and its error detection capabilities were limited. Modern protocols often employ more sophisticated checksum algorithms with improved error detection properties. While simple, the structure of the header is the foundation upon which the modern Internet functions. Section 5 Error Control and Congestion Management. Cerf and Kahn address the critical issues of error control and congestion management within their protocol. They propose utilizing checksums and acknowledgements to detect and rectify errors, ensuring data integrity. Further, they discuss mechanisms for congestion control, aiming to prevent network overload and maintain stable performance. The assertion that checksums and acknowledgements effectively guarantee data integrity must be examined cautiously. While these mechanisms effectively detect and rectify many transmission errors, they are not foolproof. Sophisticated error patterns or maliciously crafted packets might evade detection. Furthermore, the paper acknowledges that congestion control is a complex problem, lacking a definitive solution and requiring adaptive strategies. The initial congestion control mechanisms were relatively conservative, aiming to prevent network collapse. Subsequent research led to the development of more aggressive congestion control algorithms, such as TCP Vegas, which attempt to maximize throughput while avoiding congestion. The paper discusses the use of timeouts and retransmissions to recover from packet loss. Careful tuning of timeout values is crucial to avoid spurious retransmissions, which can exacerbate congestion. Choosing appropriate timeout values remains a challenging problem, particularly in networks with highly variable delay. The concept of detecting and reacting to congestion is essential for scalability. Section 6 Addressing Security Considerations. The paper offers limited discussion regarding security implications. It anticipates potential vulnerabilities and alludes to encryption, authentication, and access control mechanisms. The paper suggests that these security measures should be integrated into high-layer protocols, rather than being inherent to the TCP itself. The sparse coverage of security raises questions, particularly in light of subsequent vulnerabilities in the Internet Protocol suite. While integrating security at higher layers offers flexibility, it can also lead to inconsistencies and coverage gaps. A lack of inherent security mechanisms in TCP has necessitated the development of separate security protocols, such as Transport Layer Security, TLS, and Secure Sockets Layer, SSL, to provide secure communication channels. The paper acknowledges the potential for eavesdropping and message tampering. It suggests utilizing encryption to protect the confidentiality of data. However, the specific encryption algorithms and key management techniques are not detailed. This omission reflects the state of cryptography at the time, where strong encryption algorithms were subject to export controls. The idea of relying on higher-level protocols to provide security mechanisms has led to flexibility, but has required the creation of more protocols to maintain security of Internet data. Section 7 Addressing Implementation Details and Considerations. This section shifts focus toward practical implementation aspects, furnishing recommendations for constructing and deploying TCP within diverse operating system environments. It delves into considerations pertaining to buffer management, timer resolution, and interrupt handling, offering insights into optimizing TCP performance. The claim that its recommendations facilitate straightforward implementation across varied operating systems requires assessment. While the paper furnishes general guidelines, actual implementation necessitates careful adaptation to the specifics of each operating system. Differences in memory management, scheduling policies, and interrupt handling mechanisms can significantly influence TCP performance. The paper addresses the issue of buffer management, emphasizing the importance of allocating sufficient buffer space to accommodate incoming and outgoing packets. Insufficient buffer space can lead to packet drops and performance degradation. Adaptive buffer management techniques, dynamically adjusting buffer sizes based on network conditions, have become prominent in modern TCP implementations. The paper also discusses the impact of timer resolution on TCP performance. Finer-grained timers can provide more accurate measurements of round-trip times, enabling more precise congestion control. However, finer-grained timers also impose higher computational overhead. Practical considerations are important in implementing theoretical protocols. Section 8. Application Layer Protocol Interaction. The paper also offers insights into how application layer protocols can leverage TCP for communication. It mentions examples of application protocols that are implemented to run on TCP, such as File Transfer Protocol, FTP, and Simple Mail Transfer Protocol, SNTP. The paper discusses how these protocols exchange data through TCP connections using established port numbers. The claim that TCP provides a suitable foundation for a wide range of application layer protocols warrants validation. While TCP offers reliable, ordered delivery, it might not be the best choice for all applications. For instance, real-time applications, such as video conferencing, might benefit from using unreliable protocols like User Datagram Protocol, UDP, which have lower overhead and can tolerate some packet loss. The paper mentions the use of established port numbers to identify different application protocols. The Internet Assigned Numbers Authority, IANA, manages the allocation of port numbers, ensuring that different applications do not conflict with each other. The use of port numbers enables multiplexing, allowing multiple applications to share a single TCP connection. Application layer protocols built on TCP allowed for further development and utility on top of the core functionality of Internet communication. Section 9 Assessment of Performance and Scalability Claims. The paper suggests that the proposed protocol suite exhibits good performance and can scale to accommodate a large number of interconnected networks. The discussion regarding performance and scalability warrants critical analysis. While the initial design proved successful in demonstrating internetwork communication, subsequent experience revealed various performance limitations and scalability challenges. The paper acknowledges that the performance of TCP depends on various factors, such as network latency, bandwidth, and congestion. Extensive measurement studies have quantified the impact of these factors on TCP throughput. Congestion control algorithms play a crucial role in managing network congestion and maintaining stable performance. Scalability concerns regarding the original TCP design include limitations in the address space, routing table size, and congestion control mechanisms. Subsequent protocol extensions and architectural changes, such as classless interdomain routing and hierarchical routing, have addressed some of these scalability challenges. Over time, the Internet Engineering Task Force, ITF, is charged with continued work to improve the performance and scalability of TCP. Section 10 Reception, Criticism, and Adaptation. The reception, criticisms, and subsequent adaptations of the protocol proposed by Cerf and Kahn provide significant context for evaluating its lasting impact. The initial reaction to the paper was generally positive, recognizing its potential to address the growing need for internetwork communication. However, the paper also drew criticism, particularly regarding its complexity and the overhead associated with TCP. The protocol was further adapted into the Transmission Control Protocol Internet Protocol, TCP/IP, which has become the dominant protocol of Internet communication. Subsequent revisions and extensions to TCP have addressed various performance limitations and scalability challenges. The development of new congestion control algorithms, such as TCP Reno and Cubic, has significantly improved network performance. The introduction of IP6 has expanded the address space, addressing limitations of the original IP before addressing scheme. The paper's legacy can be seen in the pervasive use of TCP/IP throughout the Internet. The protocol's flexibility and adaptability have enabled it to evolve alongside the ever-changing needs of the digital world. Although the protocol has been updated and improved, the underlying method of the 1973 paper has become a standard for modern communication. Section 11 Conclusion: A Timeless Architect for the Future. In conclusion, the 1973 paper, A Protocol for Packet Network Intercommunication, by Vinton, Cerf, and Robert Elliot Kahn, represents a watershed moment in the history of computer networking. While certain claims concerning performance, security, and implementation simplicity require nuanced interpretation in light of subsequent developments, the paper laid the foundational principles for the architecture of the modern Internet. The concept of packet switching, the hierarchical addressing scheme, the reliable data transfer mechanisms of TCP, and the gateway-based internetwork architecture all contributed significantly to the success of the Internet. Subsequent research and development efforts have refined and extended the original protocol, addressing performance limitations, scalability challenges, and security vulnerabilities. The enduring significance of the paper lies in its elegant design, its adaptability to evolving network technologies, and its profound impact on global communication. The work stands as a testament to the vision and ingenuity of its authors, whose groundbreaking ideas continue to shape the digital world we inhabit today.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.